Guys, so I don't know if you guys remember this, but a long time ago I proved this formula using complex numbers and stuff. And today I had to sort of revise this whole thing because I was dealing with something which dealt with the same sort of um, you know integrand, except it wasn't really an integral; it was a summation. And what I found is that you can't approximate as a Riemann integral and then like solve that and get the same thing. Instead, the summation is giving you a different curve, and so I'm going to solve that summation by a similar method what I've done over here. In fact, I suggest you read this PDF because I'm really just not going to go over this. I'll just skip to the main things. So the thing is that you write this sine of nx upon sine x using complex exponentials. So you set z equal to e power ix, and then you write this as a summation, and you square that, and so that square is so the square of this quantity that we know is going to be a finite sum of these complex exponentials. But you can also write this by Taylor expanding the other form for this summation, the more easier to write form, which is z power n minus z power negative n upon z minus z power negative n. Square that, and once you square that, you have this term over there. You have to expand that using Taylor expansion, and you get this thing. And so this is really just something that you can do for only a certain range of z, but we are going to do this without really caring about anything. But it's completely okay because z is e power ix, so we can in fact do this. And so now that we have done this, right, so e power ix is magnitude 1, and so 1 minus z squared to the power of negative 2. If z square is not 1, then this number you can sort of write it like that. Yes. Right. And so this just gives us, so you can also think of it like this, that you find this polynomial for small z's, but then since you have the polynomial now, you can also use it for all z because it's an identity in the end, right? Yeah, and so now you expand this, and then you figure out, okay, so the first row, all the terms in the first row are going to cancel in any case, because they have corresponding terms in the other two rows. And so the first few terms of the lower two rows which are not cancelled, those are really what we have to deal with. And so you just have f of z equal to minus 2 summation, so these two summations, which are the sums from these two rows, right? And so now with some basic algebra, you can write this thing, sine square of nx upon sine square of x, that's equal to n plus this summation, and this is where we are going to start. So previously, to prove the integral identity, I just integrated this and found the thing, which was straightforward. But now we have to sum this, and not exactly this, but instead of x, we'll have something different. So what we are interested in is this summation. So it's sine square of n pi by 2n k upon sine square of pi by 2n k. So pi by 2n k is basically our x over there. And so we want to sum this up from k equal to 1 till n. And we want to prove that it's approximately this thing. So small n and capital N both are really big numbers, right? And so we'll start doing this. So first thing we do is that this 2 cosine of all that, we can write this using the real part function. And so it will be the real part of z power rk, where z is e power I pi by n. And so you can check yourself, this does work, right? Because supposed to be cosine of 2rx, so instead of x you are going to put pi by 2n k, right? And so this just becomes pi by n times r times k. So this works out, right? So from this you can easily get that, okay, it's the nth, so it's the nth root of negative 1, right? So basically the 2nth root of unity. And so now summation from k equal to 1 till n of z power rk, which is this term, So you can bring this summation inside of this summation, right? And n minus r is not having the k in it, so that can be pulled out. And so it's just the summation of this stuff, this cosine stuff. But then you can put the real part, and then it becomes this quantity. So the real part of summation from k equal to 1 till n of z power rk, that can be written like this. It's -1 if r is odd, and it's 0 if r is even. So that is very easy to see, and it shouldn't take you much trouble. But now that we have this thing, we can easily write our s of n, because now we just have to sum this from k equal to 1 till n, this thing, right? So summing this part is easy, it's just n times n, and summing this part is also doable now because the two real thing, so that sort of disappears. And so now you just have this thing, -2 summation all the odd terms from 1 till n minus 1, of like so the summation is of n minus r. But now with a bit of manipulation, you can write this as n times n minus 1 by 2, this summation particularly. But okay, this thing you have to approximate as the full sum, so I don't like doing this, but doesn't matter, because we're going to be dealing with large n in any case. And so this just gives us this approximation. S of n is approximately n times capital N minus n square by 2. So there's some extra fluctuation terms which I am not really going to care about. So yeah, and this is really useful because because I had to derive all this while I was dealing with something in statistical mechanics. So it really is useful. Like, this stuff comes in handy when you're solving physics problems, at least. So that's it. I'll see you guys in the next video. Bye.